This is Lab 3, Black Hole Orbit. In this lab, we started with known motion of a star, and from that calculated the net force acting on the star, and from that calculated the mass of the object exerting the force on the star. In this case, the object was a black hole whose mass was determined to be 3.978 times 10 to the 31st kilograms. We were given a CSV file with the x and y coordinates for the position data of the star. Each consecutive row is the data for the star 86,400 seconds, or 1 day, after the previous row. The mass of the star is 4.6347 times 10 to the 27th kilograms, and the position of the black hole is as shown. As with previous labs, this lab involves a lot of repetitive calculation, and so, in order to help us compute all those calculations in a timely fashion, we use Python. Here I'm showing where I entered the position of the black hole, the mass of the star, and our delta t in our code. But how do we use this information to find the mass of the black hole? Like we said before, the first step is finding the net force that's acting on the star. We know that the net force is equal to dp over dt, which is approximately equal to the change in momentum over the change in time. In order to do this for all of the position data that we have, we resort to Python. First, we find the initial and final velocities using indexing of the CSV file mentioned earlier on in the code. Then, using those values, we find the initial and final momentum by multiplying the star's mass by the initial and final velocities, respectively. Then, in order to calculate the change in velocity and the change in momentum, we just subtract the final minus the initial for each. Then, in order to calculate dp over dt, we simply divide delta p over delta t, because, like we said earlier, they are approximately equal. We also said that the net force is equal to dp over dt, so we can throw that into the code as well. The next thing that we have to do is assume that the black hole is the only force acting on the star. Then we can use the equation, the net force is equal to the gravitational constant times the mass of the star times the mass of the black hole divided by the distance squared. We can easily put this into Python as well, so that way it calculates it for us. In order to get a better visual of how the force is acting on the star, we can break it up into components. We know that quantitatively the net force is equal to dp over dt, which can be broken up into its parallel and perpendicular components, each quantitatively equal to the parallel and perpendicular components of the net force. I make a point to say quantitatively because we must remember that dp over dt and its components are the result of the net force and its components. So while they have the same numerical value, they are two different things. So, using the product rule to differentiate, we can enter the calculations for dp dt parallel into Python. We do that here. Then we can find dp dt perpendicular by subtracting dp dt parallel from dp dt. We also say that fnet parallel and perpendicular are equal to dp dt parallel and perpendicular respectively because of what we mentioned before. When we run our final code, this is what we see. Also, it prints out the mass for us right here. So our final mass is approximately 3.98 times 10 to the 31st kilograms. As long as the black hole remains in the same position and our star travels in the same path, we will always find our mass to be this. And because we were able to check the mass with WebAssign and it was determined to be correct, we know that our model doesn't fail in any way in order to predict the mass. That's the end of Lab 3. Thanks for watching.